Okay, let's begin. So, these are the remaining examples to get through for trig sub. We're going to quickly knock them out and move on to the topic at hand. Lots to get through, so we want to get through these quickly. So the next topic I'm going to teach you after this is called partial fractions. Now, while in general it's not the most difficult thing around, it's going to take a long time for me to describe how it actually works. So let's not waste any time and jump into it. So, you guys spend the weekend with these guys, so you should have some pretty good input here. Go, what do we do here? Huh? Yeah? Yes.
Do we start with the trig sub?
Start with the trig sub. Of course, you consider basic rule, all that stuff. Substitution's not going to work because you don't have an x, right? So if you let u equals this, your d is going to be 2x and you don't have it. So trig sub is probably what you want to do. What is the appropriate one?
X is equal to...
Right, so x equals a tangent theta. In this case, your a is 1, so just x equals tangent theta. Your dx is what you find next. And then you're going to go plug that in. So your dx you replace with this. And in the denominator, you have tangent squared plus 1. That is secant squared. But that's the third. So this cancels laws of exponents. And then, right, so it becomes integral of 1 over secant. How do you integrate 1 over secant? Right, just cosine. Integral. Positive something. So that is the answer in thetas. How do we get it in x's? Triangle, right? So draw the triangle. There are other ways to do it, but it's probably the nicer way to do it. Here you think of the x as x over 1, which is opposite over adjacent. So it's this, sum of the squares square rooted is that by Pythagoras' theorem. So you'd be able to figure out that sine of theta is going to be opposite over hypotenuse. So it's x over the square root of x plus 1. And so that is the answer for the whole integral, x over the square root of x plus 1. Now it turns out what we're going to do in the next section could actually attack this integral, but so far we don't know it yet. So probably the best game in town at this point is Trig. Right, x equals radical 3 secant theta. Your dx is going to be and now what we want to do is we want to change limits. And at this point, I'm going to give a very high recommendation whenever doing a definite integral by trig sub. Always change the limits. It's going to save you time. Always do this. So if you have a definite integral, now you guys learned in Calc 1 that in general you kind of have options whether you want to change the limits or not. You can either leave the old limits, do the back substitution, and then plug in the old limits, or you can change the limits and plug in the new limits into the U version of the answer. But for trig sub, I would say always change your limits. It is going to save you time. You won't need to do it in the triangles or any back substitution, and because that's just an extra 2 or 3 minutes right there if you're not really good at this stuff. So how do you change the limits? How do you change the limits? What do you use to change the limits? Right, so you have x is equal to radical 3 secant theta, and so when your x is 2, this means you have 2 is equal to radical 3 secant theta, which means that 2 over radical 3 is equal to secant theta, which means cosine of theta is radical 3 over 2. What does that tell you theta is? R to 6. Right? So it's one of those things that you have to remember from pre-calculus and maybe repeat it a little bit in calculus. But it's the value of the trig function at special angles. If you don't remember all that stuff, in Math 195 lectures, we go through trig in lectures 21 through 25. We're going to go on to x equals radical 3. This would mean that your radical 3 is equal to radical 3 secant theta. In other words, 1 is equal to secant theta. In other words, 1 is equal to cosine theta, and that tells you that your theta is 0. So the new integral is going to be, when x equals radical 3, it's 0. When x equals 2, it is pi over 6. So it's going from 0 to pi over 6 up. Now I'm going to plug everyone in. This is going to be 3 secant squared minus 3. So underneath the radical, this is going to be 3 tangent squared. The denominator here is going to be radical 3 secant theta. And your dx is going to be radical 3 secant theta tangent theta. So this cancels. And then I have radical 3, and then this would give me a tangent times a tangent, that gives me tangent squared. From 0 to pi over 6. How do I integrate tangent squared? Integral of secant squared. 0 of 1. So this becomes tangent pi over 6 minus pi over 6 minus tangent of 0. 0 and 0, so that's 0. What is tangent of pi over 6? Huh? What is tangent of pi over 6? Radical 2 over 3?
Radical 3.
Radical 3 over 3. It's 1 over radical. Right? Because sine of pi over 6 is a half, cosine of pi over 6 is radical 3 over 2. You divide them, you get 1 over radical 3, or radical 3 over 3. So that's the answer here. Been on. I think I like this. I should start off with more space right here. So these two are already done. J, let's move to the side a little bit, create some space here. Copying this one. One of the copies doesn't follow this one. That's gonna be nice. All right, how did you attack that one? Completing the square. What do you do to complete the square? Factor out the minus 1 because you need a positive 1 to complete the square, and then you just complete it inside the parentheses. So it's x squared plus 4x be a complete square. You add half of this squared, which is 4. Subtract it again because you don't want to change the value. This part here is your complete square. Let's say x plus 2 all squared. And then minus 4, but then you distribute the negative. And so your integral is going to look like the square root of positive 4 minus x plus 2 squared. And how do we deal with that one?
X plus 2 equal to times. Put 2 times the integral.
So minus,
Oh yeah, it's minus.
so it's sine. So you could do x plus 2 equals 2 sine theta. Your dx would be 2 cosine theta d theta. Plugging into this guy, you would have 4 cosine squared on the bottom, times you would have dx is 2 cosine theta d theta, and this actually cancels all of that, so it's just integral of 1 d theta. And so that's just it. So let's see. And theta is your sine inverse
X plus 2 over 2.
of x plus 2 over 2.
Can you do that by substitution method too?
You could do that by substitution if you know that, hey, that kind of reminds me of this formula that Jhevon forced me to memorize. It almost looks like that. You could actually get that done. What you would have done is there's a square root here of 4 minus x plus 2. What you could do is factor out the 4 to make it look like a 1. Again, remember your formulas are templates to apply the rule. You have to look exactly like what the rule says. So I need a 1 here instead of a 4. I can get that by factoring it out. It's going to be factoring out a half here. And underneath I'm going to have 1 minus x plus 2 over 2 all squared. And I can do a u sub here. So I would get my du is equal to 1/2 dx, or I would get 2 du is equal to dx. And when I plug that in now, I would have 1/2 the integral of 2 du over the radical of 1 minus u squared. The 2's would cancel, and so you get 1 over the radical of 1 minus u squared. That looks exactly like the rule, so that would become your sine inverse of u, and your u is x plus 2 over 2. So you could have done it that way as well. At this point, completing the square is the first step you'd want to go with, but after that, you could either do a trig sub or use a previous formula. Alright. Okay, how'd you do this one? Huh? What would you substitute?
U is equal 4 minus u squared.
Right, so regular substitution, wouldn't do a trig substitution in this case, because I would have thought of regular substitution before that, and the regular substitution is actually going to work here, because if I do that substitution, I get my x dx right there. So a regular substitution would work here. I wouldn't do a trig substitution, although if you were going to do a trig substitution, you would say something like x equals 2 sine theta, but it'll take you a longer time to get to the answer. You would have a more complicated integral, and you would also need to do a whole triangle thing to do a back substitution. By doing this, the integral now becomes minus du, well, u du over u. So you just have to integrate 1 du, which is, and after that, I don't need to do a trig back substitution. So that integral is pretty easy, and at the same time, switching back to x's are going to be easier. So let's do u is the square root of this.
When the numerator is up, do you use substitution rather?
Well, let's get through the next example, and then your question is naturally going to come up. We'll deal with it there. Well, how would you deal with this one?
I use substitution.
You use regular substitution again? That makes a lot of sense. I concur. I would say u squared is equal to x squared minus 3. My 2u du, differentiated both sides, is 2x dx, or my u du is going to be x dx. Now you might say, well, I don't have x dx, but this one you can write as x squared times x dx. And so now you realize this whole thing here is u based on my substitution. This whole thing here is du dx based on this substitution. And now I have this x squared left over. What's that? Well, I can use this equation to solve for x squared. X squared is going to be u squared plus 3. So I'm going to plug in these substitutions over here. So this is going to replace that. And this is going to replace that. And of course my x squared, I have all these colors. I haven't used yellow in a while. My x squared is going to replace that. So I'm just going to boop, 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 swap those guys in. And so this integral is going to look like u squared plus 3 times u du divided by u. I use cancel. And then it's just the power root. And my u is the square root of that guy, so this is going to be x squared minus 3 to the 3 over 2 power over 3 plus 3 times the square root of x squared minus 3. So now to deal with your question. So this, of course, is the section on trig substitution. The last two examples, though, they're much better dealt with the regular substitution. So now the question is, when can we do that? When is that an option? When do I know that I don't need to go through a trig sub, a regular sub is going to work? So trig sub or not the trig sub? That is the question. Based on all the examples we've done, and particularly paying attention to the last two, what would you say a rule of thumb would be?
Numerator is up. Like 3.
Yeah, you'll notice that in both of them. In the last one, it was just an x over something, and in this one, it's an x cubed over something. Yes, that is the trick. Basically, if you have an odd power, so do not trig sub if you have a positive odd power x as a factor. It can technically work even when you have a negative odd power of x, but again, you're going to need another technique to kind of deal with that. So basically the idea is trig sub versus regular sub. So I see an integral like this, x squared over the square root of 4 plus x squared. That's a trig sub integral. If I see x cubed over the square root of 4 plus x squared, that's a regular substitution integral, right? So it's like x squared or x to the 4th, x to the 6th, x to the 10th, trig sub, right? Because if I do a regular substitution, I'm only going to take off one of the x's with that substitution, and I'm going to have an odd power of x left over, which is going to force a radical in there. It's actually going to get messier. Whereas with this guy, once you plop off the odd power, 1 power of x, you have an even power left over, and then you can write x squared as some other even power. Even if it's very large, so you can think of something like x to the 7th. Basically what's going to happen is you'd say something like u squared is going to be 4 plus x squared, and then you'd be able to solve for x squared. Well, this is going to be 4 minus u squared. What is going to happen here, you can think of this as x to the 6 times x, and how do you find x to the 6? Well, you cube both sides of this. Multiplying that out by the binomial theorem, which I'm sure all of you are very familiar with and can do mostly in your head at this point, you get a very easy integral that you can do via the power rule. So I would tend to avoid trig sub if there's another odd power, there's an odd power of x to help me out. And in practice, I'm not going to give you a huge odd power. I'm not going to do like 213 or anything like that. But you know, in principle, you can avoid trig substitution easily if there's an odd factor. If your x cubed is in the denominator, it's not so easy to pull it off. A regular substitution would put you in another situation where you might need another technique, namely the technique we're about to do right now. So that ends what I wanted to do from trig sub. You kind of know everything you need to know there. It's just a matter of practice at this point. Moving on to 8.5, we're going to talk about integration by partial fractions. Let's start with a motivating example. So consider this integral over here, x squared minus 5x plus 6x. You see that integral pop up. You want to compute it. With what we know so far, best approach be? Well, it's not a basic rule. Can't really simplify it to look like a basic rule, and it's not really in the right form to do a trig sub, which we would know how to deal with. One thing you could do is complete the square. Which would look like x minus 5 over 2 squared. Square that, you get 25 over 4, so you want 6 minus 25 over 4, which is 26 over 4, minus 25 over 4, which is 1 over 4. So this would be, where's the 24? So it would look like that. And you could have done, at this point, x minus 5 over 2 is equal to 1/2 secant theta. And you can continue. And at this point, probably like me, you're thinking, yuck, don't want to do that, right? You don't want to have to go through a trig substitution and with fractions all over the place. It's can be very annoying. Trig substitution is great and all, but sometimes it's just annoying to actually get through it. And the whole back substitution process is kind of tedious. Then if there are limits on the integral, you're going to have to remember all your You know, there are some drawbacks to trig substitution. It's powerful enough as it is. Here's a better way. What I want you to note is that this integral, the same guy over there, I can actually think of it as this integral. And you can actually check if you were to combine these two fractions here, create the common denominator or whatever. X minus 2, this would be 3 minus x, the x's cancel, and so you get 3 minus 2, you get 1 on top, and you multiply these denominators to get a new denominator. X minus 3 times x minus 2 multiplies out to this guy. So yeah, these are exactly the same integral. Now, of course, the difference is that one has a lot of advantages. I can actually integrate these guys very easily. Technically, a substitution happens here, but it's kind of easy to do it in your head. Because your du would equal to dx, so there's no constants to divide by. So yeah, that's the answer. And so, yeah, what this guy here is called the partial fractions of this guy over here. So pretty much when you take a larger fraction and you break it up into a sum of smaller fractions that add up to the larger fraction, you say you found the partial fractions of that original expression. Okay? Now, and the process to go from this situation to find the partial fractions, finding the partial fractions, this is called partial fraction decomposition. So you can say I performed a partial fraction decomposition of this function, and I found its partial fractions with that, and this big, mean, nasty integral transformed into a bunch of smaller little integrals that are easier to deal with, and so I can actually compute this integral by computing this integral, and that would be your answer. So that's basically partial fractions. Everyone get it? All right, cool. All right, moving on to the next section. How do you do this? How did I get from here to there? And you might say, I know what you did. You typed it into Wolfram Alpha, and you wouldn't be wrong, but I could have done it without it. And that's what I'm going to teach you to do, how to do it with. Yes, I understand that. Just sit down. How do you do this? Why am I still writing a 3? It's actually it's not so bad. It's just going to take a long time for me to actually explain, as I was saying before. Let me tell you. So, first, when can we do this? Are you always able to find partial fractions for any fraction that I would give you? And the answer is no. So, when can you know that this technique is even a viable option? Or when do you know that, yeah, I'll be forced to do a trig sum or something like that? So, this technique works if, 1, you have a proper rational function. Now remember what a rational function is. I mean the technical definition of a rational function, a ratio of two polynomials. You have one polynomial divided by another polynomial. And proper means that the highest power of the numerator, degree of numerator, is smaller than the degree be proper. So here, the degree of the numerator was 0, the degree of the denominator was 2. So this is a proper rational function, right? If I had an x squared plus 4 on top, it's no longer proper. If I had an x cubed minus 7, no longer proper. I could have had 3x plus 5, that would be proper. Yes?
Can you divide it up though? I think I left it. Like divide it so that we have like 1 or 2 or whatever and then
Yes,
proper.
you can. I'm going up to that, right? But the actual process of finding a partial fraction decomposition cannot start until you have that situation. So the point I want is you have to recognize when what you're looking at is not proper, because then you might have to do something like a long division to get it into a certain situation. But you can't actually start it without having this. The second thing that you need is that the denominator can be factored over the rationals. Now, for those of you who are going to take a class like complex analysis, that's not going to matter. You can factor any polynomial into a bunch of linear factors, but I'm talking about factoring in the sense that you learned in pre-calc, right? So it means all your coefficients are rational numbers, meaning fractions, and you can break them down as far as you can, as you learned in like a class like Math 195. So the denominator you need to be able to factor the denominator, right? And luckily for this one, you could actually factor the denominator. This actually factors into x minus 3 times x plus minus 2. So that's what you need. As long as these two situations hold, you can apply this technique. Now it might not be the best technique, I'm not saying it's the best technique, but it's viable, it's doable. Now let's talk about how-to. Another process that you're going to have to know. So step 1. Make sure the function is proper. If not, make it so. So I declare you to be proper. No, you have to actually compute it by a couple options here. Algebraic manipulation, meaning multiplying and dividing by something convenient, maybe factoring out something and canceling something in a convenient way, adding or subtracting something convenient. I'm going to teach you a very common technique that can work here, or polynomial long division. So I'm just going to give you a quick example of polynomial long division. I'm not going to teach polynomial long division because you learned that in Math 195. You forgot about polynomial long division, and the quick example that I do today doesn't jog your memory. Go watch the Math 195 lecture on polynomial long division. You don't have time in this class to actually get into it. So you need a proper rational function, and the denominator needs to be able to factor. So the step 1 is to actually check that you have a proper rational function. If you do not have one, you would need to try to make it into one using one of these two techniques. Here's an example. Suppose I had x equals 1 over x squared. Now that is a rational function. However, it is not proper. The highest power on the denominator, on the numerator is 2. The highest power on the denominator is also 2. The power on top, the highest power on top, is not smaller than the highest power on the bottom. It's not proper. So here's one way that you could actually deal with this. So a common technique, usually useful, is to get the denominator in the top. Make necessary corrections. So you're going to want to get the denominator in the numerator. How do you get the denominator in the numerator? Well, you just put it there, right? So I'm just going to say x squared plus 2. I want that to be in the numerator. So you write that down. However, of course, you didn't start out with an x squared plus 2. You had an x squared plus 1, which means you putting in that x squared plus 2 changed the value. You need to make the necessary corrections so that you get back the original value. How can I correct this to get back the original value?
Minus 1.
Subtract 1. So I throw the denominator into the top, and then add and subtract whatever I need to get it to be what its original value was. Now do you see what you can do? You can now split the fraction across the numerator. You can split it into two parts. So that first part is going to be x plus 2 over x plus 2, which cancels and becomes 1. And then you're going to be left with minus. So this fraction is equal to that fraction. This part here is now proper. And in fact, if we were talking about integrating this thing, we could actually just integrate here without any further technique. That's going to give you an x. That's going to give you like an arc tangent. Right? Like a 1 over radical 2 arc tangents over radical 2 with a substitution. That's one way to actually do it. Another example, to kind of piggyback off this one, not much different. Let's say you had that. So you could do the same sort of thing. First, you factor out an x to get that x squared plus. First, you factor out an x to get that. And again, I would just put in the denominator in here. And then I can, again, split it. So this is going to be x times x squared plus 2 over x squared plus 2 minus x times 1 over x squared plus 2. That cancels. And so this would become x minus x over x squared plus 2. So I started with a fraction where the highest part on top is larger than the one on the bottom, and I reduced it to a bunch of fractions where that is no longer the case. So that's not a rational function. At least we won't need like any crazy technique to integrate that. This one is also easily integrable with a regular substitution. So if you had to integrate this, pretty much write it like that and integrate that. And that's using algebraic manipulation. Questions on that? So. Polynomial one. So I'm just going to do an example of one of these two so you can see I get the same answer. Which one do you want me to do? Yeah?
So if I use the division method and I get the remainder plus that, is it going to be the same answer as this, or is it different?
Well, yeah, they have to be the same. I mean, because it's math. You shouldn't get something different if you do something mathematically valid. Right? This is just a rewriting of that. You can think of this as a simplification of sorts. Right? So you're definitely going to get the right answer. The same answer either way. Which one do you want me to do?
Second one.
You want to do the second one? Okay. So you want to do polynomial long division. Here's how you do it. The guy on the bottom is called the divisor, and he goes out in front. You do this thing here, and you write down the guy underneath, under there. Now, one important thing that you have to remember is that you have to, starting at the highest power, you have to account for all powers going down. So while they don't show up, you definitely want to hold a place for the x squared and the constant place. So you start with an x cubed. There are no x squares, so you either leave a space or write 0x squared. Then you have 1x. There are no constants, so you put a plus 0, right? Everything is going to need to line up, right? You want to put the different powers of x's all in a certain column, so you have to expand. If you put the x right beside this, it's going to get crowded and you're going to get confused and you're going to mix something up. So make sure the guy that goes underneath here, you line him up. So the guy that's on the bottom, you put out here to the left. The guy that's on top, you put underneath here. And make sure you account for all powers counting down. Then what you're going to do is you're going to take the first guy here, divide into the first guy there. x squared divided into x cubed goes how many? Goes x. Then what you're going to do is you're going to take that x, you're going to multiply everybody here, and then you're going to put the result under here. So x times x squared gives you x cubed. X times plus 2 gives you 2x. Make sure you line it up in the x column. And you're going to subtract that line from the lines above. X cubes die. Then I would have plus x minus 2x. So minus x is the result. So now what you would do is you say x squared into x. Well, you can't. That power is smaller. So you stop the process there. So now this guy here is called the remainder. This guy here is called the divisor. And the guy up here is called the quotient. And your answer is going to be the quotient plus the remainder over the divisor. And it's always what it's going to be. So in this situation, what you would get is the quotient plus the remainder, which is minus x, over the divisor, which is this guy. And you'll notice that that's the same answer. So you can either go through long division. Long division is a more general algorithmic process. You can always do this way, as long as you can always do this way. Okay? If you notice any little quick tricks, you can do this. It'll save you. Depending on how quick you are, this necessarily won't save you some time, but it'll definitely save you writing space. Because to do long division, you have to go to the side, you do your own little thing working down. So it'll save you writing space if you know how to do this. But if you don't, it's okay to just know how to do this. At minimum, I would say know how to do this. This will cover many more cases. So even situations where you can't really see a nice way to simplify, this one is going to work out for you. So yeah, that was step one. Step one is to make sure that the thing you're looking at is a proper rational function. If it's not proper, do either an algebraic manipulation to get it, very commonly get the denominator in the top, or you can do a long division of polynomials. And like I said, don't remember any of this stuff. It's in pre-calc. You can watch my Math 195 lectures. Let's move on. Step two. You're going to factor the denominator completely. So here, I mean factor in, again, in the sense that you learned in Math 195. So I expect you to remember all your factoring techniques, difference of squares, difference of cubes, sum of cubes, AC method, factor by grouping, all that good stuff. So. By the way, including, there's a theorem called the rational roots theorem. I do expect you to know that and know how to apply it. Do it in pre-calc. If you don't remember how to do that, if you don't even remember what the hell are you talking about, go watch my Math 195 lectures on dividing polynomials. So that's an important theorem that's going to help you when all other factoring techniques fail. This is like your last hope to kind of get something to factor. It will involve you figuring out what the factors are and then afterwards applying a long division to finish off the factoring process. So know how to use the rational roots theorem to factor something. Not really going to say anything else about factoring. Like we do tons of factoring. In algebra, in pre-calc, in Calc 1, you're doing tons of factoring all the time. You need to remember all of that stuff. Step 3. Okay, so now we're gonna do a few examples here because this is very important. Like this is This is where the process all begins to take shape. Break up the large fraction into smaller ones,
You know, the angle, you know.
where the denominators
What is that identity?
are the factors from
Yeah.
step 2. The numerators are, I want to say generic, so they're going to be like some generic polynomials. You're not going to know exactly what they are at face value. Are generic polynomials of 1, specifically 1 degree less than the denominator. Okay. So, what are you talking about, Jhevon? Let's do some examples. Example. Let's say you have something like 5 over x times x plus 2. So that denominator is fully factored. That is a proper rational function. What you're going to do is you are going to break this fraction up into 2 separate fractions, where the denominators are each of the factors from here. So x is a factor, x plus 2 is a factor. You break it up into 2 fractions where x and x plus 2 are the denominators. Now, how do you create the numerators? Your numerators are just going to be your generic run-of-the-mill polynomials, of course, with arbitrary constants for the coefficients that are 1 degree less, specifically 1 degree less, always 1 degree less than the denominator. Now, the degree of the denominator here is what? 1. So the degree of numerator must be 0. What does a 0 degree polynomial look like? Just a constant. But you don't know what the constant is, so you just put a letter, A. A represents an arbitrary constant. Similarly here, the degree here is 1. The numerator needs to be 0 degree. So that's some other constant, B. Here's another example. 7 over x times x squared plus 1. Now, until you get to complex analysis, that cannot be factored. So this is a fully factored denominator, right? So now there are 2 factors. So again, you're going to break this up into 2 parts. Again, the factor here has a degree 1, so the numerator must have degree 0. Over here, you have degree 2, so the top must have degree what? 1. How do I write something that looks like bx plus c, right? Do not reuse the a because you don't know ahead of time that those 2 are going to be the same numbers, right? So you use different letters, right? So if it's quadratic on top, it needs to be quadratic on the bottom, it needs to be linear on top. If it's linear on the bottom, it needs to be a constant on top. Let's just throw a cubic in there just for the nice mix. So if I have x times x cubed plus 7, like there's not a nice way to factor that over the rationals. So you'd actually break this up into x over x cubed plus 7. Here's a. Here,
Bx squared plus cx plus b.
you guys getting it? Okay. So make sure it's proper. If not, do the long division to get it proper. Once it's proper, factor the denominator. Once the denominator is factored, you're going to create separate fractions for each denominator. The numerators must have 1 degree less than the denominator. Now, there is a little bit of nuance to this process here, so let's put step 3b, sort of a refinement on step 3. If any factors are repeated, and repeated just means you have like you don't have one factor of x squared plus 1, you have like 2 factors of x squared plus 1, 3 factors of x squared plus 1. It's called a repeated factor. You must further break it down into separate fractions, counting up to the multiplicity. And that's a technical phrase for multiplicity. It's a technical phrase which basically means you're going to count, you're going to repeat this factor over and over. You're going to start at power 1, then power 2, then power 3, and you're going to count up to the multiplicity of whatever the largest power is. So for example, let's say I have 17 over x times x plus 1 squared. So again, you'd have, break it up into x, you break it up into x plus 1, but you notice you have 2 factors of x plus 1. How do you deal with that? Well, you break it down further by having another x plus 1, and that one goes to power 2. Of course, this is going to look like a, b, and c. Because the numerator follows the inner factor, the main factor. That's linear, so the top needs to be a constant. If you instead had, if you instead had something like 12 over x times x plus 1 cubed, what that would look like is, well, a over x plus b over x plus 1 plus c over x plus 1 squared plus b over x plus 1 cubed. So that's a repeated factor. You need to count up to that factor. Yes?
If you had like x squared plus 1 cubed, what would be the numerator?
That is a good question. Okay, 17 over x times x squared plus 1 cubed.
A over x plus bx plus c over x squared plus 1 plus
dx plus d. fx plus g.
plus fx plus g.
The powers of fractions.
The what?
The powers of fractions.
The powers?
So instead of saying 2 to the third, it's like 2 over 3.
If this was like 2 over 3,
Yeah.
then it's not rational in the first place. And this whole process is a non-starter. Right? So it needs to be a proper rational function to be even starting it. If you have a non-integer power, it's not rational because it's not a polynomial at that point. At that point, if this is like a 2 over 3, then it's now a trig subproblem. You wouldn't do this. So we only do it for proper rational functions. Now, part of that might seem like, why would we do that? So here's kind of the idea. Let me illustrate with this guy here. If you had something like 17 over x plus 1 squared. Now, if you follow step 3, part A, technically what you'd want to do is, because there's a quadratic on the bottom, you want a linear function on top. But what is an appropriate linear function? It turns out, to get things to simplify nicely, we just think of x plus 1 as the new variable, not x. So I write a times x plus 1 plus b. Right? So I don't just write ax plus b, I write that whole thing. Because my hope is that will make it simplify. If I just think of that, I just shift the x to kind of coincide with the denominator, because hopefully I'm thinking things are going to cancel down the road, etc. And then this will actually break up. Now, of course, this cancels that. We'll get a over x plus 1 plus b over x plus 1 squared. Right. So by following step 3, but doing it in a more convenient way, you're allowed to break down the fraction even further. So whenever a factor is repeated, Basically, you're going to repeat it. The numerator is going to follow the inside fraction, right? So it's still linear here. So you're still going to have just constants on top. But because it's repeated, you count up to the multiplicity. Just add all these fractions. So that is step 3D. Any other questions about that so far? Right? Because this whole process, you're going to have to put all these steps together, right? And of course, I'm going to give you guys examples where we're doing that. But right now, just one by one, make sure you understand each individual step in this process. Then we're going to put it all together eventually. Now, step 4. This is going to be the final step, but it can be an important one. We're going to find these guys, just like integration, they're called arbitrary constants. Now sometimes, like in the quiz, I wrote down the bonus, you don't need to find the arbitrary constants, but most of the times you will need to find the arbitrary constant. If it's like, you need to compute something, you need to know what is A, what is B, that's going to get this all to work. You're going to find the arbitrary constants. There are 2 main methods. And they may be mixed and matched. So you could exclusively do one or the other, or you can sometimes do one, sometimes do the other in the same problem. It kind of depends on the situation. Most of the times I would mix them together. I tend to like the first method more, so if I can get that to work, I'm going to try to get it to work. Okay, so method 1. Let's start by looking at the example that started this whole discussion. Let's look at something like that. Right? I broke that down into 2 fractions. How did I figure out what those fractions had to be? Well, that is a proper rational function. My next step would be to factor the denominator. This factors into that. Okay. Then, going on into step 3, I would break this up into x minus 3, x minus 2, a and b. Okay. So here's where, so this is from step 3, would bring you here. So here's where this method kicks off. Step 1, multiply both sides by denominator on the left. So denominator on the left is this guy. We're going to multiply the entire equation by that guy. Now clearly on this left side, the entire denominator is going to be cancelled, and I'm just going to be left over with the 1. On the right side, in the first factor, the x plus 3's are going to cancel, and I'd be left with a times x plus x minus 2. In the second term, the x minus 2's are going to cancel, and I'd be left with b times x minus 3.
Wait, I'm sorry, could you go over that one?
Multiply both sides by the large denominator on the left. I'm going to multiply both sides by. So I multiply both sides by x minus 3 times x minus 2. It's like I'm clearing denominators with the LCD. So a different part cancels on each one of these terms, and I have that as a new line. So 2, plug in convenient values for x. Now, sometimes you're able to solve for a constant right away, sometimes not, or you can set up a system of equations. Now, when it comes to convenient, the gold standard for convenient is the following. What is the most convenient thing that exists? Well, it is going to be a number that is going to kill all the arbitrary constants except one of them. Right? So, for that example, can you think of such a number?
2.
X equals 2. So I can take x equals 2. Right? This equation must hold for every value of x. So I'm going to plug in x equals 2 here. what's going to happen is I'm going to get 1 equals a times 2 minus 2 plus b 2 minus 3. Of course, that's going to die. And I will just have 1 equals minus b, or in other words, b equals minus 1. And I can plug in another convenient value, like 3. Again, super convenient. That would look like a times 3 minus 2 plus b times 3 minus 3. So now that's going to die. And I'm going to have 1 equals a, so that's my a. And so therefore, so I have a over x minus 3, well my a is 1. And I have b over x minus 2, and my b is minus 1, so it's minus that. And I've now written this fraction as a sum of smaller fractions. So that's method 1. Clear denominators by multiplying both sides by the LCD, and then plug in convenient values. Now, of course, the most convenient are the guys that can eliminate people, but technically this method could have worked if you had plugged in other values. So if you had plugged in, say, x equals 1, right? You would have gotten 1 equals minus a minus 2b. And then you could have plugged in x equals 0. And then you would have gotten 1 equals minus 2a minus 3b. And now that's a system of equations. You'd still be able to solve that for a, b, and c. So not all the time you'd be able to outright eliminate everybody, but this method can still actually work by you setting up a system of equations and you just solving that again using algebra methods.
Professor, why don't you multiply a times x and a times minus 2, and then I should drop that in.
That is method 2. So this was method 1. So what you're kind of thinking is method 2, which I'm going to describe to you now. So this is one option, one approach that you can take to actually finding the a, b, and c's. The other option is, as you say, to kind of multiply things out and group like terms. So let's look at method 2, and we can compare it to this. Now, which method you choose is totally up to personal preference. Whatever you see first, whatever you feel more comfortable with, do that. And forget the other one. Personally, I use both of them at the same time sometimes, but I try to get method 1 to work, because for me, my brain, it works easier that way. But method 2, so same guy. First step, is it proper? Yes. If it wasn't, I would have done long division, blah, blah, blah. Okay. Step 2, factor the denominator. Step 3, break that up across the denominator. Okay. Now, for method 2, the first step, same as in method 1. So, I would get 1 equals a times x minus 2 plus b times x minus 3. Except this one, the second step is different. It's going to say multiply out and group like terms. Then what you're going to want to do is equate coefficients. It's also a very common phrasing that you'll hear. Equate coefficients of like terms. We use that phrase all the time to mean this sort of process. So what we would do here is this is going to multiply out on the right, so it's going to give us 1 equals ax minus 2a plus bx minus 3b. I'm going to group like terms. So the x's are like terms. This is a plus b x. And these guys have no x's. Those are like terms. So this is minus 2a minus 3b together. So I group like terms. Now what I'm going to do is I'm going to equate the coefficients. Notice what you have here. Of course I have x's over there. Do I have x's over here? Technically yes. There are 0 x's over there. So I really have 0x plus 1 on the left side, and I have a plus bx plus minus 2a minus 3b on the right. And at this point, what you do is you equate the coefficients. So it's an equation, which means the amount of x's on this side must be equal to the amount of x's on that side. So a plus b must be equal to 0. Similarly, the constant term on this side must be equal to the constant term on that side. So the minus 2a minus 3b must be equal to 1. So what you would get here is a system of equations. So this method always ends up with a system of equations. A plus b is going to be equal to 0, and minus 2a minus 3b is going to be equal to 1. And at this point you can solve that by a variety of methods. You can use substitution or elimination. If you're going to be an engineer or math major, I'd probably say err on the side of doing elimination all the time. That'll make linear algebra go a lot nicer for you. But in this case, I'm just going to do a substitution. A equals minus b. This would mean minus 2 times minus b minus 3b equals 1. So this ends up being minus b equals 1. So you end up with b equals minus 1. And since a equals minus b, a would be positive 1. And so, again, I get the fraction x squared minus 5x plus 6 is going to be, well, it's a over this. My a is 1. Plus b over that, my b is minus 1. There are your partial fractions. Examples for next time. Examples to work on for Thursday. Also notice that college is closed on Wednesday. So if you have Wednesday classes, don't show up. It's also closed on the following Monday. Eventually one of our classes is going to be replaced by a Monday class to make up for this. But for now, don't show up on Wednesday or Monday next week. Examples. So find the partial fraction decomp of these guys, and we'll go through them in class on Thursday. So 5x squared plus x plus 6. On Thursday, I'm also going to show you a nice trick that can work sometimes it's called the cover-up method. That's going to be really cool. It'll allow you to do some of these problems like you're a ninja or something. How do you do that so quick? And they're setting up their A's and B's.
For A, does that say 5?
Come again?
For letter A, does that say 5x squared?
Yeah.
This? Yes. It's really annoying when they use s's as variables for stuff, because my 5s, when I'm writing them quickly, they look like s's. It makes Laplace transforms annoying in differential equations. So they normally use s. So try those. So next time I'll show you another cool way to find constants in certain situations, and then we're going to go through these. And then we're going to do some integrals using this technique. So I will see you on Thursday when we go through that. And I'll give you your quizzes on Thursday as well. I had them graded, but I forgot to record something. So.